Hi guys, this is section 1.1b, logic statements and quantifiers. Today we're going to be using the red, the blue, the purple, the green, and I think that's it today. Alright, so today we're going to continue our discussion on logic statements and quantifiers. So we talked about for all statements on the previous lessons, and we also talked about statements in general, where statements are always true or always false. So universal statements. Universal statements are statements asserting that a certain property holds true for all elements in some set. May involve more than one variable. All right, so universal statements are statements that mean everything, like for all, not just for some. So for all integers, for all real numbers, for all natural numbers, whatever the case may be. So write using symbols for all real numbers. So I don't know if you learned this in Math 1 or not, but for all real numbers, the double back R is the symbol we use for real numbers. Back when I taught Math 1, I did teach my students the symbol for real numbers, but you may not have. And a lot of people put their little double back closer together, but it's okay. All right, so hopefully you remember for all, okay? For all is the upside down A. For all real numbers, A and B. So when we go to write this, we can do for all A and B in real numbers. Okay, it says A plus B squared equals A squared plus 2AB plus B squared. And P of A and B equals A squared plus 2A plus B squared. So what they're saying is that A plus B squared equals P of A of B. Okay? Because P of A of B is this piece. All right? Now, part B of this says, state whether P of 87 and 13, what it is, and tell whether it's true. All right, so let's see. So it's saying that A is 87, B is 13. So what we're going to do is do 87 plus 13 and square that. So 87 plus 13 is 100. 100 squared is 10,000. Okay. Now, so you might want to get your calculator out today. Let's see if my calculator's charged. And it is. That's really good. And then we're going to plug it into the a squared plus 2ab plus b squared. So a squared, 87 squared plus 2 times 87 times 13 plus 13 squared. So I put parentheses around the things that got plugged in here. So 87 squared is 7,569. And we'll do this middle piece. 2 times 87 times 13 is 2,262 plus 13 squared, which is 169. So 169 plus 2262 plus 7569 is 10,000. So when it says state something, that means work it out. And is this true? Yes, it is. Okay, the next definition is counterexample. Counterexample, the definition of that is proves a universal statement false. Okay, and you don't have to come up with a lot of them. Notice it says counterexample, not counterexamples. Okay, so you only need one thing that does not work. Okay. Now, the next thing, it says, is the statement, so it's already saying it's a statement, is it true or false? And then it says justify your answer. So what you're going to do here to justify your answer is give a counterexample if false. Okay. Another thing we're going to do is we're going to write each of these statements in symbol form. Okay. Right, using symbols. So we're going to write all of these in symbols. So let's just go ahead and do that first. For all real numbers, for all x in real numbers, x squared is greater than x. For all integers x, so for all x in integers, 1 over x is less than 1. Okay. Now, the other one is for all people. Let's do this. For all people in the room X. Let's just go with that. People in this room, and if you're watching this video, you're having to imagine a normal classroom setting. X is a gray stone student. Okay? Alright. So the first one. For all real numbers x, are all numbers that are squared greater than the original number? Okay? And a lot of times when they're talking about numbers being greater than or less than, if you think of fractions, that would be your counterexample. Okay? So, the answer to this one is false. Because, let's do 1/2. If you square 1/2, you get 1/4. 1/4 is not greater than or equal to 1/2. Okay? So same thing here. Let's look at this one. For all integers x, 1 over a number is greater than 1. Another rule of thumb is, if you're not using fractions, and you could put a fraction in here and make it a funky fraction and do keep, change, flip, but you could also put in a 0 here. This is undefined, so that doesn't work at all. You cannot have a 0 in the denominator. Okay, so undefined is not less than 1. It doesn't even exist at all. So this would be no. Okay, you could also put a 1/2 in the denominator here and then do keep, change, flip, where you leave the 1 alone. Change this to division and flip this to become 2 over 1. So that'd be 1 times 2, which is 2. 2 is not less than or equal to 1. So that would also work. So let's use something that's not math related. For all the people in the room X, X is a Greystone student. And that would be false. Because Mrs. Evans is not a student. Now, so we've talked about universal statements where you say for all. So universal statements say for all. Existential statements, and if you have your highlighter, you can highlight the terminology we're learning today. So universal statements, counterexample, existential statement. Okay? Alright, so existential statements. At least one element of a set for which a property holds true. Okay, so earlier we said the following universal statement was false. For all real numbers x, x is, and this should say x squared, sorry. X squared is greater than or equal to x. Then that's equivalent to saying the following is true. The phrase there is or there exists is called a quantifier. Okay? So you could say there exist X in real numbers such that X squared, and when you do change it from an universal to existential, and you have a symbol, you flip it, and if it has equal to, you take it away. So you do the opposite. Okay? So this symbol means there exist. Okay? So we would write a backwards E. That means there exist X in real numbers for X squared is less than X. Okay? So we're going to do an example of these. Another example of this. All right. There exists a Greystone student in the room. We need to write that in symbols. Okay. So there exists X in the room such that X is a Greystone student. And you're going to see that when you use there exist after the comma, you use such that. It's kind of like if and then. When you put if here, you put then here. When you put there exist here, you have such that here. Okay? Now, what's the difference between universal and existential? So universal is true for all in a set, and existential is true for one or more in a set. Okay, so let's look at these statements that are written in symbols here and see if we can figure out if they're true or false. And if they're false, we have to justify our answer by giving a counterexample. Okay, there exists in, what does this mean? Integers. So there exists an integer such that when you square it, it gives you 5. So integers are whole numbers. Can you square a whole number, positive or negative, to give you 5? No, you can't. So this one's going to be false. Okay, because the only thing you could square to give you 5 is the square root of 5, and that's not an integer. So n would be square root of 5, which is not an integer. Because remember, when you square a square root, it drops it away. They cancel each other out. So that's the only thing that could go there that would give you 5. Okay? There exists in real numbers, so there's a real number such that the square root of, such that n squared is 5. Now, real numbers, that can be anything as long as it's not imaginary, as long as it doesn't have an I on it. So this is a real number. So this one is true. Square root of 5 is a real number. Okay, so let's summarize what we've learned the past 2 days over universal and existential. Okay, so in universal, the form is for all x in S, P of x. Okay, this is just an example. The form for existential would be there exists an x in S such that P of x. Okay, so for all, there exists such that. So the quantifier, the part that makes it universal, are the words for all. Okay. Existential, there exist. Okay. The symbol for all is the upside down A. The symbol for there exists is the backwards E. Universal is true if everything is true. If true for everything. Here, existential, this is true if true for at least one thing. Okay, so we've learned about universal, we've learned about existential, we learned what a counterexample was, we've learned what symbols for integers there exist, for all real numbers. We've learned all those symbols. So now you're going to have assignment. So if you have any questions, please let me know. Thanks.